Alright, so Koko the monkey needs to eat all these banana piles before the guards come back. We need to find the minimum speed that lets her finish in time. Here's the thing, the answer itself lives in a range, and that range is sorted. If speed k works, then k plus 1 definitely works too. That monotonic property? That's screaming binary search. Instead of searching through an array, we're binary searching on the answer space itself. Super elegant. So what's the slowest Koko could possibly eat? 1 banana per hour, that's our left boundary. And the fastest she'd ever need to go? The size of the biggest pile, because eating faster than that gains her nothing, she still spends 1 hour per pile minimum. So our search space is 1 to max of piles. We also initialize result to right because we know that speed always works. Now we enter our classic binary search loop. Each iteration, we pick the middle speed k, that's our candidate eating speed to test. Think of it like Goldilocks trying different speeds. Is this one too slow, too fast, or just right? We keep narrowing until we find the sweet spot. This line is where the real work happens. For each pile, we calculate how many hours Koko needs at speed k. If a pile has 7 bananas and she eats 3 per hour, that's ceil of 7 divided by 3, which is 3 hours. We use math.ceil because even if there's 1 banana left, she still spends a full hour on it. We sum that up across all piles to get total hours needed. Watch what happens when hours is less than or equal to h, that means speed k is fast enough. She finishes in time. So we save k as a potential answer, but here's the key insight, we're greedy, we want the minimum speed. So we move right down to k-1, searching the left half for something even smaller that still works. And if hours is greater than h? Koko can't finish in time at this speed, she's too slow. So we need to speed her up by moving left to k plus 1. We're eliminating the entire left half because anything slower would be even worse. Classic binary search elimination. Once the loop ends, result holds the smallest k that let Koko finish in time. Every time we found a valid speed, we saved it and kept looking for something better. When left finally crosses right, we've exhausted all possibilities and result is our optimal answer. Time complexity is O of n times log m, where n is the number of piles and m is the max pile size. The log m comes from binary search, and for each candidate we do an O of n scan. Space is O of 1, just a few variables. The big takeaway here? Whenever a problem asks for the minimum or maximum value that satisfies some condition, and that condition is monotonic, binary search on the answer. Absolute game changer of a pattern.